Okay. Hello everyone. I'm Yukihiro Tagami, a research engineer in Yahoo Japan Corporation. I also have been a doctoral course at Kyoto University. Today I'm talking about AnnexML, approximate nearest neighbor search for extreme multi-level classification. So at the beginning, I'd like to show you a summary of my talk. The theme of this work is about extreme multi-level classification. For these classification tasks, we propose a method called AnnexML, which is a k-nearest neighbor classifier with graphs in the embedding space. AnnexML improves the trade-off between prediction time and accuracy, more accurate and faster. First of all, we present three types of classification tasks: typical binary classification, and multi-class classification, and multi-level classification. On binary and multi-class classification tasks, we choose single label from the candidates. On multi-level classification, however, we can choose multiple labels. In this example, both cat and bird are selected. Traditional one versus rest approach converts the multi-level classification into a set of binary classification tasks like this. So this transformation makes a set of binary classification tasks with the number of labels is the same as that of labels. Next, we introduce extreme multi-level classification. This is a multi-level classification with extremely large number of labels and has recently been receiving much attention. In this work, we tackle the problems with 10,000 to 1 million labels. So traditional one versus rest approaches are computationally expensive in both training and prediction. Because the number of binary classification tasks is extremely large. In one example, extreme multi-level classifier is run to tag a new Wikipedia article by using a subset of the most relevant Wikipedia categories, like this. So in this work, for extreme multi-level classification, we present a graph embedding method called AnnexML. AnnexML tackles three problems that SLEEC has. SLEEC is a state-of-the-art embedding-based classifier. So AnnexML improves both prediction accuracy and speed. This figure plots the prediction time and accuracy for Wiki LSSTC dataset when changing the number of ensemble runners with different random initialization. Horizontal axis represents prediction time in logarithmic scale. Vertical axis represents prediction accuracy in terms of precision at 1. So upper left line indicates better results, faster and more accurate. Proposed running methods improved prediction accuracy. In addition, approximate nearest neighbor search technique speeded up the prediction time. As a result, at the same level of accuracy, AnnexML was up to 58 times faster than SLEEC. Of course, AnnexML achieved better results than recent tree-based methods. Before representing the details, we show our notation. N, M, and L are the number of training examples, features, and labels. So training data, feature vectors, label vectors, and classifier are represented like this. AnnexML make a prediction by using k-nearest neighbor classifier in the round embedding space like SLEEC does. The idea of training procedure of AnnexML is simple. The training points that have similar label vectors are allocated closer in the embedding space. In addition, we speeded up the prediction procedure by using an approximate nearest neighbor search technique. Next, we present overview of training. Each point in the space represents a training sample. First, training samples are connected if two samples have similar level vectors. Then, hyperplanes are run to divide the graph into k subgraphs, while keeping the structure as much as possible. In this example, k equals 3. This partition aims to make both training and prediction faster. So, projection matrices are run for each divided subspace in order to allocate connected samples closer in the embedding space. For a given test point, we make a prediction with k-nearest neighbor classifier in the embedding space. Since we constructed embedding space to allocate samples that have similar levels closer, k-nearest training points to a given test point in the embedding space are expected to have similar levels. Using the round hyperplanes, we determine to which partition a test point belongs to. In this example, a test point belongs to partition 2. So the test point is projected into embedding space using the matrix V2. Then k-nearest neighbor in the embedding space are obtained. The empirical level distribution of the k-nearest neighbor is returned, just averaged level vectors. We propose 3 improvements of AnnexML to SLEEC, 2 for prediction accuracy and 1 for prediction time. First, we introduced the learning to partition data points. While SLEEC uses unsupervised k-means clustering for this purpose, AnnexML utilizes level similarities between data points. As noted before, AnnexML makes a prediction by using k-nearest neighbor classifier in the embedding space. Thus, for accurate prediction, we should allocate 2 training points that have similar level vectors into the same partition. So we regard this problem. As k-way minimum graph cut problem, and construct k-nearest neighbor graph of level vectors. The computational cost of naively finding k-nearest neighbors for all data points is n squared. However, since level vectors are typically sparse in this problem setting, we utilize embedded index to find k-nearest neighbor efficiently. But in some cases, unfortunately, computational cost remains n squared, even if we employ embedded index. So we ignore some head levels and approximately construct k-nearest neighbor graph. Head levels means the levels that most data points have.
Question. Is the feature space embedded continuous words or binary? One feature per word?
Yeah. Sorry?
Is it one column per word?
Let's hold the questions to the end of the talk.
Okay.
In general.
Sorry. Okay. After constructing a k-nearest neighbor graph, we want to obtain hyperplanes that divide the graph into k subgraphs while keeping the structure as much as possible. In contrast with the common balanced k graph cut problem, we need to run a merge-class classifier to predict the partition of an unknown test point. So we sequentially maximize this objective function for each training point, like stochastic k-means clustering. So CI is a cluster assignment indicator for ith data point by using the current weight vectors. First term is intended to assign approximate nearest neighbors to the same partition CI. approximate nearest neighbor of ith point to the same partition Ci. Second term aims for randomly selected points to not be included in the partition Ci. In other words, this term makes each partition includes almost the same number of data points. Last term is L1 regularization term to obtain sparse weight vectors. Second, we represent how to run embeddings. We have defined the relevance score as cosine similarity between embedding vectors zy and zj using projection matrices VC. We also present the conditional probability by using our relevance score, our cosine similarity, and the softmax function. Xk is randomly selected from data points in the partition C. Gamma is a scaling parameter. To run the projection matrix VC, we minimize the negative log likelihood. The above negative log likelihood is transformed like this and optimized by using SGD with adequate running rate scheduling. Lastly, we present an approximate nearest neighbor search technique by using graph structure for fast prediction. For prediction of AnnexML, we want to efficiently find nearest training points in the embedding space. First, a test point traverses a board tree. Then, the indexed points are obtained as a reasonable approximate nearest neighbors. The nearest neighbors of the nodes are added to a list of candidates. We start to improve the approximation quality by local search. The blue nodes represent approximate nearest neighbor nearest points at this time. The white nodes are candidates to be evaluated, and black ones are already evaluated nodes. So local search are, yeah. After all candidates nodes are evaluated, the approximate nearest neighbors are returned, these two nodes. Using these procedures, since we only need to calculate the distances to a small number of balls of centers and subset of training points, we can speed up this search task. Now we describe the dataset used in experiments. We compare the AnnexML with some recently proposed methods on the 6 large-scale public datasets. The number of levels ranges 13,000 to 600 of thousands. Suffixes of dataset names indicate the number of levels, 30,000 or so. We evaluated performance of methods with precision at K. These metrics are widely used for extreme multi-level classification and ranking tasks. Larger value is better. We also evaluated the performances with NZCZ at K, but since the results showed the same tendency, we only report P at K. This table shows experimental results. The bold elements indicate the best performance of methods. AnnexML performed the best in almost all cases. There were especially large improvements for datasets that have larger level space. This table compares the 3 proposed improvements of AnnexML. If we did not use proposed running to partition method, we use the simple unsupervised k-means clustering method like SLEEC does. We also did brute force cosine calculation instead of approximate nearest neighbor search. Method E, only using method to run embeddings, outperformed SLEEC on almost all case datasets. The proposed partitioning method improves prediction accuracy. And approximate nearest neighbor search method had slightly poorer accuracy. Next, we present the speed up effect of approximate nearest neighbor search technique. These figures plot the prediction time and accuracy. For fair comparison, these experiments are conducted with C++ implementations on single CPU thread or with the same machine. So upper left line indicates better results, faster and more accurate. AnnexML represented as blue lines, achieved good results on almost all datasets. AnnexML BF represented as green lines, which AnnexML BF is a variant of AnnexML which does brute force cosine calculation, not using approximate nearest neighbor search technique. So comparison between AnnexML and AnnexML BF shows that approximate nearest neighbor search successfully speeded up prediction time without a noticeable drop in accuracy. Finally, I'd like to show you a summary of my talk again. For multi-level classification with extremely large level space, we propose a method called AnnexML, which is a k-nearest neighbor classifier with graphs in the embedding space. AnnexML improves the trade-off between prediction time and accuracy. As a result, at the same level of accuracy, the prediction time of AnnexML was up to 58 times faster than that of SLEEC. At this Yahoo Japan research page, C++ implementation of AnnexML is available. If you are interested in AnnexML, check it out. Okay, I gratefully acknowledge them for insightful discussion and helpful comments. Okay, thank you very much for your attention.
Let's thank the speaker.